In this video, we will talk about logarithmic differentiation. And I want to motivate this with an example. So this says, let y be x to the x squared. All right, and I want to find dy dx. So I have this function that has a variable in the base and in the exponent. So there are two rules that may come to mind with something like this. One of them is the derivative of x to the n, the power rule. But it turns out I can't use that. I can't use the derivative of x to the n just being n times x to the n minus 1, since to use the power rule, the n must be a constant. It must be just some fixed number. But in this case, my exponent is something with a variable in it. It's definitely not a constant. All right, so I'll put a sad face. All right, that would have been nice if I could have just done power rule and brought the power down and subtracted 1, but unfortunately I can't. The other thing that might come to mind is, wait, we have this rule for the derivative of a to the x. The derivative of a to the x. Remember, this was ln of a times a to the x. All right, but I can't use this either. We can't use this derivative, since in this formula, the base of the exponent has to be a constant. Since the a must be constant, in our function, it's not. In our function, the base is x, and that's a variable. It's not a constant. Okay, so these two formulas that we have don't work. So here is what we're going to do. So we will take the ln of both sides and simplify with log rules first, before we take any derivative. With log rules. All right, so we will get ln of y equals ln of x to the x squared. All right, and on the right-hand side, I can use the log rule that says, well, if I have a power inside of a log like this, I can move it to the front. All right, so I'll get x squared in front of that log, x squared times ln of x. And on the left-hand side, we'll just have ln of y. And now I have this equation, and the y isn't isolated anymore. So the output variable, the y, is defined implicitly. So maybe let's try implicit differentiation. So implicit differentiation. All right, so let's take the derivative of both sides now. We're going to take d dx of the left and d dx of the right. So we'll take d dx of ln of y and d dx of the x squared ln of x. And on the left, because these variables are different, this is a y and that's an x, I'm going to have to apply chain rule here. Okay, so the derivative of ln of some stuff is 1 over the stuff, and then times the derivative of that stuff, and the derivative of y is dy dx. On the right-hand side, the variables are the same, so this is just a normal derivative, and I'll need product rule. I'll get the first function times the derivative of the second, the derivative of that ln of x, which is 1 over x, and then plus the second function, the ln of x, times the derivative of the first, and that derivative is 2x. Okay, all right, so we have dy dx, and I'm going to isolate dy dx, so I'll multiply the y over to the right-hand side to get rid of the 1 over y. So I'll get y times the whole right-hand side. I can cancel one of these x's to be left with an x, and then I get plus 2x ln of x. The final thing I'm going to do is I'm going to plug back in for what y is, because my original function was completely in terms of x, so it'd be nice to get the derivative completely in terms of x. So dy dx, remember at the start of the problem, y was my function, x to the x squared. So I'll have that times x plus 2x ln of x, and that's my derivative. That is the derivative of the function x to the x squared. So this is this technique is called logarithmic differentiation, where we take ln of both sides and then differentiate implicitly to get our derivative. All right, so this technique, logarithmic differentiation, logarithmic differentiation is helpful for functions that are hard to differentiate. I'll just abbreviate differentiate directly. Like this one was actually impossible based off of what we know to differentiate directly, but actually maybe no comma here, but simplify nicely with logs. So things that simplify nicely with logs, I want to write some examples, are things like powers, products of things, because we can use log rules on products of things, and quotients. When you divide two things, there are nice log rules for that. All right. And the example that we had here was one of those. I had x to the x squared, so involve this power. Another tip-off that I wanted to use logarithmic differentiation here is that there were variables in the base and the exponent, because we didn't have a technique yet to handle variables in both spots. So in terms of our goals for this section, we finished our last goal, recognizing when and how we can apply logarithmic differentiation.